this is a great command. You can come to this output and get a lot of valuable troubleshooting information. First and foremost, is the interface up? Yes. If the interface is not up, you're not going to form a neighbor adjacency. The interface might be participating in the OSPF process, but if it's up, down, or down, or administratively down, you can't form a neighbor adjacency. So it has to be up. You can even verify your link local address for this particular interface. So if you are experiencing routing problems where you can't reach a particular next hop IP address, remember the next hop IP addresses are link local addresses, well, you can always come to the interface here and see, is that the correct link local address for the interface that I'm supposed to be sending packets to? We can verify the area the interface belongs to. In this case, it's area 567, the process ID that it's been attached to. And we can verify the router ID again. So a lot of repetitive information from other show commands that we can have here. So everything we've already seen, we can double check here if we want to as well, except for reference bandwidth and some of the other options. But network types, same. We still have broadcast, non-broadcast, point-to-point, point-to-multipoint. And just like we discussed with OSPFv2, some of them require designated routers, some of them don't. Some of them have timers of 10 and 40, while others have different timers, 30 and 120. Therefore, if we expect to form a neighbor adjacency, the network types should match between neighbors. If they don't, then they should be network types that have the same features, same concepts. For example, they both need to be able to form designated router, or they both need to use designated routers as an example, and they both have to have the same timers. If they don't, you're not going to form a neighbor adjacency. You can verify the cost. You can verify the state. In this case, we are the backup designated router on this particular multi-access link that we're on. Priority of the interface. We can see who the designated router is based on its router ID of 192.7.7.7. And its link local address is FE80:75. And then the backup designated router has a router ID of 192.5.5.5, and that just happens to be us, as we can see here. And the link local address is FE80:57, and that does match up with our link local address right here. So it's a good thing it matches. Hello intervals, dead intervals are listed right here as well. So if you are, again, troubleshooting timers, this is where you go to troubleshoot your timers as well. And then down at the bottom, we can see we have a neighbor count of 1 out this particular interface, and it is with this particular router, 192.777, and it is the designated router in this particular case. So let's look at the output of show IP OSPF neighbors. So I want to see who my neighbors are. And in this case, we can see R5 has neighbors with R4 at the router ID 192.4.4.4 and the router ID of 192.777, which is R7. Priority is 0 in this case for the neighborship with R4's priority is 0 because in this case we're using the point-to-multipoint OSPF network type on the serial interface between R4 and R5, and therefore there is no designated router election process, so the priority is 0, and that's why we see the dash. We are full, meaning we've fully exchanged our information that we need to exchange for the link state databases. We are happy. Notice the dead timer is exceptionally high here in this particular case on R4, and that's because when you're using the point-to-multipoint, the dead timer and hello timer are higher. So let's take a look at that really quickly. Show IP OSPF interface serial 1/0. We can see in this case our hello is 30 and our dead is 120 seconds in this particular case in time. And our state is point-to-multipoint, as we can see. Go back to the neighbor output. We don't specifically see the interface number. For example, fast Ethernet 2/0 or fast Ethernet 2/1 or serial 1/1 of the neighbor like we do with OSPFv2. And there's multiple reasons for that. With IPv6, But the biggest reason is because of the fact that we can have multiple IPv6 addresses on a single interface. So since we can have multiple IPv6 addresses on a single interface, instead of identifying a router by that physical interface itself, we use interface IDs instead. So in this case, our 4's interface with an interface ID of 3 is the interface that they are using to send hello packets to us and form a neighbor adjacency. So instead of specifying the actual interface value in there, like serial 1/0, like we have with OSPFv2, we are seeing an interface ID value instead. And our 7's using its interface, which has an ID of 11 in it, in order to form a neighbor adjacency with us. If we look here, this is our local interface that we utilize in order to reach that particular neighbor.